We can now begin looking at forces more mathematically or quantitatively instead of previously when we only look at them kind of conceptually, a little bit fluffy, you know. And in order to make that leap, though, we want two tools under our belt. And one of them is ability to analyze vectors, and the other one is to be able to use free body diagrams and use vectors on them. Vectors are really simple concepts. They are a type of quantity that have a magnitude and a direction. So a force, for example, or velocity, those are all vector quantities. And that's opposed to scalar quantities, which only has a magnitude and no direction. That's like mass or speed, those things are all scalars. On paper, on a diagram, we represent vectors as arrows. So say I had an arrow like this, all right, that's a vector because it has a direction, and I'm going to give it a quantity. We'll call that 5 newtons. Now, this wouldn't be very helpful if you want to analyze it mathematically, because we need both a diagram to show us the direction and a number to show us the magnitude. Now, we want to be able to combine these two pieces of information into one number. And to do that, we enlist the help of coordination systems. Basically, if we set up a coordination system arbitrarily, call right as positive, in this case, we can now say that 5 newtons, if you write positive 5 newtons, given that coordination system, we know that this would mean 5 newtons to the right. So conversely, if I had a similar something like this, and that's, say, 4 newtons, I would be able to say that's 4 newtons, negative 4 newtons. And that alone can tell me both the direction and magnitude because of the coordination system. Alright, so we're going to be using this concept later on, but first let's turn our attention to the free body diagram. A free body diagram is a diagram, of course, that isolates an object in the universe to show all the forces acting on that object. So note that we're not showing the forces that the object exerts on anything else, but only the forces that everything else exerts on the object. So I have a couple of steps over here, all right, that we're going to go through and use on this example. This is a dinosaur getting pulled by a person, and it is moving towards the right, all right, across the floor. The person really isn't that important. It is just the source of the force that is exerted by that rope over there. Oops. So we can really throw him away. All right, not really that useful. All right, let's look at the first step. And this is where my old high school teacher used to tell me something interesting. He said physicists look at objects differently, just like how Neo looks at things differently in the Matrix. They look at it in terms of the object's center of gravity. So instead of looking at the entire dinosaur, we're going to shrink it down into a box or a dot usually, but in this case I have a diagram, so it's cool, I can shrink it. We shrink it down to the center of gravity. Okay, first step, check. Next, we set up a coordination system just like before, but in this case, since we have both an up-down, so that's a y, or left-right, which is x, directions, we want something in the 2D. So we want both up-down and left-right, so both in the y and x directions. We have coordination system, and we say that's positive. We're good. Next, we'll draw in the forces as vectors, so the arrows. Once again, like before, we're just using the same concept. We have the tension force. That's equal to 200 newtons. I'm just going to give you numbers right now. Some of this actually you probably can analyze. We have the weight, because anything with mass is weight. And if I gave you the mass, you should be able to calculate for weight. So it's a very light dinosaur. Once again, the normal force. That's 50 newtons. And you have the friction, which you should be able to calculate once again if I gave you the normal force and something else, coefficient of friction. So this is a very strange situation we have here because the friction is greater than the normal force, which we won't really see much. But anyways, now we have arrows and numbers which represent magnitudes. Once again, we want to be able to represent these arrows and numbers as one number to represent the entire situation. So to do that, we once again use our coordination system. So normal force over here is going up. So in the y direction, we assign that as positive, right? Yeah, we did. For the force of gravity, that's going down, so that's negative. For the frictional force, now this is in the x direction, we assign that right is positive, so this would be negative. Now we have a tricky business here with the tension force because it's lying at an angle. It's not on either one of these components. So in order to analyze this guy, we break it down into an addition of two vectors, and these two vectors lie on the axis. We call these two vectors the component vectors, basically. So we can say it's going this much to the right and this much up. So that is the tension force broken down into its x component, and the tension force broken down into its y component. Now if I gave you a number here over here, say it's 30 degrees, so now you have a magnitude of the hypotenuse of the triangle and a degree you can calculate for the rest of the sides, the two sides. I'm just gonna give you right now. That's 100 newtons and that's 173 newtons. And these are all positives because they're in the same direction as the coordinates. Okay, we're done. Our last step is to be able to derive the net force, which is what we really are after. Let me clean up the diagram a bit and transform it right before your very eyes. Voila! Isn't this a lot nicer? So what we do from now is we look at this and analyze it direction by direction. So first let's look at the y direction. Here we go. So we have this vector over here, 100. From that we have, okay, let's move down a bit. From that we have this over here, that's 50. And from that we come down that much. And when we add the three numbers together, so we have 50, 100, and negative 150, what we get in the end is the sum of all the vectors in the y direction. And you quickly realize, if you add them in your head real quick, that's 0. So we have no net force in the y direction. Now if we look at the x direction, we have this, that's 173 newtons, and then going back, 73 newtons. Now when you add those two together though, you realize that in the x direction, you have a positive number of 100 newtons. What does that mean? Well, according to our coordination system, that means my net force is simply this over here, this arrow over here, that's 100 newtons. If my coordination system had been the other way around, say I said up and left is positive, I would end up having negative 100 newtons, which when you translate that into a diagram, it's going to give the same arrow. So, of course, the physical world can't change because the math is wrong. Now we have the tools that we need in order to analyze Newton's 3 law problems. See you soon.